This is the first in a series of short videos going over some high points for the exam coming up. This is basically what I have been talking about for the couple of days before the exam, if we were in the same room. I did post these practice problems on D2L, and each section, there's sort of a point to it, and I wanted to just make sure the point was clear because the particular questions aren't the important thing. It's more of just the type of question. The multiple choice questions at the beginning are trying to get you to think about just what the examples we looked at, how they kind of fit into categories. So we, instead of reacting to an individual series like it's the first time we've ever seen it, try to pay attention to kind of families of examples and what they have in common. We pointed out a couple of these. Excuse me. Obviously the geometric series is an important type of example where we have a number of times powers of r that you're summing up. It's an important type of example because we know exactly when this converges and diverges, and it's the only family where we actually know what it converges to when it converges. But you might ask yourself, what happens, for example, if you use the ratio test on a geometric series, what happens? Because those are two things that we learned about, and so we should understand geometric series. We know how to use the ratio test, and we should know how that works. So, for example, up here, series D in both these cases, those are geometric series, and this question is talking about how what the ratio test is saying about the things that are up there. So it would make sense that you would know what the ratio test does to geometric series in general, and then you don't have to wonder about what happens in that particular case. The other family of series that we've talked about being a family are the p-series, and so these are when you have 1 over k to a power. Again, the sum is over k. So, for example, letter A and letter C, the one next to it, all of those things on this page, those are p-series. The letter A ones are that series when p equals 1, and letter C is p-series when p is equal to 2. A couple of things to know is that the p-series, you can, again, we know exactly when these converge and when these diverge, depending on what p is, but the analysis for all of those is done using the integral test. And so this is a very simple family of functions that all would use the integral test, meaning that if you change the problem into a continuous integral, it's easy to see when these things converge and diverge. So what we found out, if you don't remember, was that we get convergence if p is greater than 1, and we get divergence if p is 1 or less. But it doesn't really matter. You don't have to really commit that to memory. But knowing that it's just a matter of doing a simple integral test is all we need to do for it. That's really enough to know. So we know that those do. We know an easy reason why they do it. But again, what happens with the ratio test, right? Ratio test is something we learned about later on. But what does the ratio test say the p-series are going to do? And what you'll see if you try out a couple of these is that with the ratio test always says r equals 1 for for p-series. Whereas for the geometric series, it's not too surprising that in the ratio test, the r is, well, it's the r. It's the ratio for the geometric series. So that makes sense. That's why we use the letter r in the ratio test, because it does coincide exactly with what happens in the geometric series. But again, these are two large families of examples, and they account for 3 out of the 4 choices in these problems. And so knowing knowing when these things converge, when they diverge, what the ratio test would say about them, those are things that make you example smart. You should try the other ones here. I mean, other one's pretty common, like the 1 over k factorial. That's not so weird. That's the simplest thing I could think of that had a factorial in it. And again, that factorial always makes sort of the same thing happen from the ratio test. Anyway, so rather than just blindly doing ratio test problems, try to think about simple structure, simple series structures that we've looked at, and then understand what the ratio test would be doing in those cases, or which one. The other way to think about it is which ones would the integral test apply to easily. Not all of these things. The red one I circled, the 1 over k factorial, that's not going to be an easy integral problem to do. So the integral test probably is not going to be helpful for that. But anyway, so on our exam, you're not going to have to decide which test is appropriate. So the way that I'm getting at that is with questions like this, where I'll take series that we may have only studied with the integral test, and then ask you a question about the ratio test, or vice versa. So this is my way of getting at, just sort of looking at it from a higher point of view to sort of understand what families of examples are doing. I will say the harmonic series here is a really important example. Letter A, this is called the harmonic series. So that's the that's the P series where P is equal to 1. The reason it's important is because it's the cutoff. It's the very first of the P series that diverges. When we said the P series converge when P is greater than 1 and diverge when P is less than or equal to 1. So this is when P equals 1. So this is the sort of the cutoff example for the P series. And so it's important in a number of ways. One of the things that people who are first studying this often get wrong is the fact that they want to say, they want to write a sentence like this. Since the terms 1 over k go to 0, and I hope that you're listening to what I'm saying, because I'm going to put this in quotes. I don't want you to think this is true. I'm saying this is what some people would say, and this is definitely not true. This is a sentence that I see more times than you could imagine. Because the terms go to 0, the series converges. This is 1,000,000% wrong. So I'll write that 1,000,000% wrong. This is just not true. The series does not converge. It's true for alternating series. With an alternating series, if the terms go to 0, then the series has to converge. So, so this series, for example, converges because its terms go to 0, but only because it's an alternating series. So the harmonic series is a really good example of this not happening, of the terms going to 0 implying the series converges. This is 1,000,000% not right, but I'm sure some people will say something like that on the exam. It's a very easy statement to make, but it's definitely not true for series of positive terms, and the harmonic series is a really good example to illustrate that. In the harmonic series, the terms go to 0, but the sum does not converge. All right, I've went on too long about that one. I'll do a separate video for the next kind of problem.